So the first thing I want to talk about today is actually just a little bit of a pedantic point about the difference between what the book defines as standard deviation and standard error and how I talk about those two quantities. So note about the book and homework. So they define the standard deviation as specifically the population standard deviation sigma, right? So this is if I took every single data value in my whole population, that thing that we can't really do because populations are so huge. But if I did and I had every single one, I could plug it into that standard deviation formula and get out specifically this number that we call sigma. Whereas the standard error is a term that has sort of popped up a few times with regards to confidence intervals. And the book and the homework usually refer to that as, especially in the case of standard error for the population mean, refer to it as this value, this sort of population standard deviation divided by root n, which I have referred to, I think, almost exclusively as the standard deviation of the mean, right? So standard error was that thing that popped up in our confidence interval formula, but the book usually refers to this as standard error, even outside of the context of the confidence interval. So I wanted to bring that up because there was a question that I think confused some people on the homework, and it was likely because of this sort of pedantic point. If you lost the point for this particular question, shoot me an email and I'll give it back to you, because I think I didn't really like their wording on that question, and it wasn't really in line with how I've referred to these things in this class. So that was a tiny little point. I want to start this class with a little bit of a more complicated example of confidence intervals. And I hope this example, by studying it, we can all sort of better grasp how all of these different parts fit together. And I'm going to end this example with sort of a generalized formula of what I'm about to do. And hopefully, well, maybe without further ado, I should just dive in and you'll see what I mean. But this is supposed to be a more difficult approach to confidence intervals, something for you to think about. And then once we're done with this, we're going to jump into hypothesis testing. So, example. Let me set the stage. Each December, people around the world celebrate the birthday of, and let's see if I pronounce this correctly, La Virgin de Guadalupe, loosely translated to the Virgin Mary. As part of the Catholic tradition. And in fact, it's a cool thing I discovered actually just from Wikipedia, is that the Basilica of her in Mexico City is the most visited Catholic pilgrimage site in the world. Pretty cool stuff. So that's the stage. Our question has to do with, in some traditions, families go on a spiritual journey to celebrate. Suppose you know that the standard deviation of lengths of these journeys is 1 mile. So we know the population standard deviation. Your friend gives you the following 95% confidence interval that she calculated. So I have it as 8.907, 8258 to 9.49217,418. Okay? My question to you, and this is the tricky question, is what was her point estimate? Right? And what was her sample size? So these sorts of questions, ultimately, they're going to boil down to our ability to do algebra. But, well, our ability to do algebra and also our ability to know what the formula are and to recognize what we do know and what we don't know. So let's start by writing, the formula. So a confidence interval is the point estimate minus the critical value times the standard error. And the upper, so that was the lower confidence bound. The upper bound is the point estimate plus the critical value times the standard error. So we know that this is the formula. And what else do we know? We were given in the problem, so we know that sigma is equal to 1 mile. So we know that. We know that it's a 95% confidence interval, right? So we know that alpha is equal to 1 minus 0.95, okay? Which is equal to 0.05. And since we know alpha, we also actually know what C is equal to. We know it's, right? Absolute value of the alpha over tooth quantile of the standard normal distribution, which is going to be, oh goodness, I'm doing this from memory. I think it's like that. If anyone wants to check me, let me know. I didn't actually write it down, but I'm pretty sure that's it, which is just 1.9699. Okay, so we have 3 things. What else do we need to know? So we want to know the point estimate just from this confidence interval. So the first thing to notice is that, so this is the stuff that we know. We also want to notice that the point estimate, in this case, our sample mean x bar, is always at the center of our confidence interval, right? So if I were to draw this confidence interval, what it goes from around 8.91 to about 9.49, x bar is at the center because this value right here, we took the point estimate minus c times standard error to get the lower bound, and we took the point estimate plus c times the standard error to get the upper bound, right? So if we want to know, what x bar is equal to, do you all agree that if I knew it would just be 8.91 plus c times the standard error, right? I would take this point, I would add the standard error to get to where x bar is equal to. Do we feel good about that statement? So the question is, what is the standard error? And the answer is, and this is actually just a formula you can remember, or this is the margin of error. I keep calling this the standard error. C times the standard error is equal to the margin of error. I apologize. So the margin of error is equal to the width, or the total span of the confidence interval, divided by 2. Right? Because the total length was this plus this. That gives us the whole thing. So if we wanted to know that little slight thing, we would just need to take the whole width of the confidence interval and divide it by 2. So combining all of these ideas together, x bar is going to be equal to the lower bound of our confidence interval plus the margin of error, which is equal to the lower bound confidence interval plus the width divided by 2. Ooh. Oh goodness, my iPad just froze. Interesting. Okay, which is equal to, I'm just going to say lower bound to save some time, plus, what is the width of the confidence interval? It's just going to be the upper bound minus the lower bound, right? How you calculate range. All right, so that's how we would, just from knowing the confidence interval, you can work backwards to figure out what the point estimate is. So let's do this. It's what, 8.90782 plus the upper bound was 9.492 round up to 2. 8.90782 divided by 2. And here I'm going to calculate this, but if anyone can beat me and shout it out, I'll just believe you. Oop, I beat all of you. Ha ha. 9.02. Yep, 9.2. So, just knowing the confidence interval, you can actually work back to figure out what that point estimate is. So that was the first question we asked. The other question is, what is n? Right? So we know quite a number of things. We know, we knew that c is equal to 1.9699, I believe, right? We knew that sigma was equal to, goodness, what do we know sigma? 1 was 1 mile, right? And we know further that the width of the whole interval is equal to 2 times the margin of error, which is equal to 2 times c times the standard error, which is equal to 2 times c times sigma over root n. right? So if we knew the width, we could, so we know the width, we are able to calculate that. We know 2, we know c, and we know sigma. So this is actually just going to become an algebra problem to solve for this root n number. Okay? So let's see, I will times, maybe I'll times root n to both sides and get 2c sigma, like so, it's multiplication. Which means root n is equal to 2c sigma divided by the width. Yeah? Which means n is equal to look good? And I'll even write this a little bit nicer for us. The width is just the upper bound minus the lower bound. Square. So now we have a formula for n. So we can just plug it in like we did before. So 2 times, what was c? It was like 1.9699, I believe. Sigma was given to us, it was just 1. Then the upper bound was 9.49217. 9.49, oops, that was a typo. Minus 8.9078 squared. And if you were to do this, it would actually, I'm going to save us the time, but it would come out to 45. Cool. So this is a pretty good example. It makes you kind of think backwards and think about how all the things come together to make your confidence interval. And it requires that algebra prerequisite that was a prerequisite for this class. So if you got a little lost, I'm going to be posting these lecture notes like I always do. So please go through this on your own time and really make sure you understand all the steps that happened here. But the two takeaways, I guess, are the formula that I wrote here, or the formula that we developed there, and the formula that we developed right here. Okay? So this is how all of these things are interconnected. So that was our example. To motivate our conversation, our next big topic, which is hypothesis testing, I'm going to propose a question to all of you. You had read an article that the true average lengths, or length, of these spiritual journeys was 8.7 miles. Should you believe the article? So I read an article. They did not cite their sources, but they claimed, they talked about these spiritual journeys, and they claimed that the average of all of these spiritual journeys was 8.7 miles. And us, as now astute statisticians, think to ourselves, is this a true number? I don't see what your sources are. I don't know how you came up with this number. Did you just make it up? Did you actually come about it using a lot of research and a lot of thinking? Who knows? But note something very important. Our confidence interval was this. Is 8.7 inside of our confidence interval? No, it's not. So confidence intervals, recall what they are. If we were to make a confidence interval like this, take a different sample every single time, make tons of them, we would expect approximately 95% of the confidence intervals made this way to contain the true population average. So if 8.7 were the true population average, we're noting that it's not in our confidence interval, is it? So in fact, we're 95% confident that that 8.7 number isn't actually the true population average. That maybe this article didn't actually do their research very well. And this is a question I'm posing to you. These are just ideas I'm trying to float. We're now going to get a lot more precise about how I would approach a problem like this. If somebody gave me a value and I wanted to determine statistically how believable their value is. Okay? So that is my introduction to this next major topic, hypothesis testing. So, after a lot of work, we are finally ready to revisit the fourth step of our statistical process. Do you remember this? This was honestly from so long ago. But the fourth was form a conclusion. Right? The elusive fourth step. We've done all of our other stuff. We've set up our experiment. We've asked our questions. Now what do we say? And what can we say? I hope you're excited. This is probably one of the most, if not the most used thing in other fields, the most used thing from statistics by other fields. So regardless of what you plan on doing with your careers, this will likely come up. So this data, I'm going to name it runners in DC. And it's going to be our motivation for hypothesis testing. So the above data describe all participants in Washington, DC's cherry blossom run in 2012. So I'm actually going to say not all participants. I'm going to say a sample. My bad. According to the sample, the average time to complete the race was 95.61 minutes. The average time, I'm going to tell you further, to complete this race in 2006 was 93.29 minutes. Okay, so we have we have two things here. We have a sample from 2012, and from that sample we got a sample mean, which is this value, 95.61. And we know further that the actual population average of people running this race in 2006 was this number, 93.29. So we have two runs, one that happened in 2006 and one happened in 2012. And my question to all of you is, does what we observed in 2012 provide strong evidence that runners are faster or slower than they were in 2006? Oh, and I want to actually extend this. I'm going to put a little caveat. So faster or slower than they were in 2006 versus the possibility that there was no change. Okay, so let's note here that it's looking like, just based on our sample, that runners are slower in 2012, right? We observed by our sample an amount of time, an average amount of time that took longer than it did in 2006. So our initial thought is, it might not actually be the same anymore. The population parameter may have changed. But recall, every single time we take a sample, we get a different X bar. So maybe it's not actually because the population parameter changed, but rather just because of the random variation associated with X bar. So to determine whether it is truly a change in the parameter, truly a change in the actual average running time of people who run this race from year to year, or if it's just random variation, we use the following formulation. So H0 is, and I'm going to talk to you about what H0 is. We call it our null hypothesis. I'll give you a definition of that in a second, but I want you to see it first. The average 10-mile run time was the same for 2006 and 2012. So we call that, this is H naught, H sub 0, the null hypothesis. And this, called the alternate hypothesis, or H sub A, is the average 10-mile run time was different um, 10-mile run in 2012 was different than that of 2006. Okay? And note that all three possibilities are represented here. So we have that they are the same. So versus, we said we wanted to know, are they faster or slower or no change, right? And the null hypothesis here is the no change option. And the alternate is just says different. So different could mean a lot faster, they got a lot faster over these years, or they got a lot slower over these years, right? So all these options, no change, faster, or slower, they're all kind of represented in this framework, in these two possible hypotheses. So now that I've thrown hypotheses at you, let me actually define them. So definitions, we have two. The null hypothesis which we denote as H naught or H sub 0, represents either a skeptical perspective or a claim to be to be tested. Alternatively, the alternate alternative. Did I spell that right? No, I did not. I meant to say alternative. Alternative hypothesis, which we denote as H sub A, represents an alternative claim under consideration. And is often represented by a range of possible parameter values. And also, I'm going to say recall, in our case, by parameter, I mean the population average, the unknown value associated with our population, in this case, as the average. Okay. So something to note here is that this is an innocent until proven guilty situation. So our null hypothesis represents sort of, I'm skeptical that there has been a change. I want to make the hypothesis that I currently believe, and we're going to test to see whether or not it's true. And the statistical approach to this sort of problem is to take the innocent until proven guilty approach. That you assume the thing that you're trying to test is correct, and unless the data tells you very strongly otherwise, you will continue to hold on to that null hypothesis. And I'm going to show you how that works. So, going back to our example, let mu be the population the unknown population parameter, population average of running times in 2012. Our hypotheses can then be written as H naught, that mu is equal to 93.29, and HA, that mu is not equal to 93.29. So note, let's maybe take a step back, look at our original question. We wanted to know if the average time to complete the race in 2012, the true unknown population parameter, was equal to the thing that we knew was true in 2006. We knew it was 93.29, and we want to know if it's still 93.29 or if it's changed. So that's really what we've represented right here with our hypotheses. We have this thing called the null hypothesis, the skeptical position that, okay, it hasn't changed. In 2012, it's the same as it was in 2006. And we have this alternative hypothesis that says, if we look at our data and it says, it doesn't really appear like the population parameter is the same, then we would instead reject the null hypothesis and say, actually, I don't think it is 93.29 anymore. I think it's different. So this is sort of a formulation of our question as to whether or not the running times have changed between the years 2006 and 2012. So I need to do a quick, because I'm going to refer to it in this way, I need to do a quick definition before I actually show us how to perform this hypothesis test. And that is, here, we call 93.29 the null value, since it represents our population parameter, here the population average, when the null hypothesis is correct, right? So this value, this thing that mu is equal to under the null hypothesis, I will refer to it as the null value. This is just a quick definition. And also you'll see this in the future. They'll say, oh, is it the null value? And they're referring to whatever mu is equal to under the null hypothesis. All right, so let's actually do this. Testing a hypothesis. So step one, formulate your question. In our case, it was, is mu equal to, is the population average in 2012 equal to 93.29, or is it not? Okay, so step one, just write down what you're trying to prove or disprove. Step two, take a sample, right? Before I even started, I decided what question do I want to answer. And now I go out and sample a bunch of runners, and that in this case, this has already kind of been done for us by, well, frankly, me. We discovered that our sample average was 95.61. And as mentioned, this sample estimate suggests that the average time was actually longer in 2012. But we should ask ourselves, is this just due to the random variation associated with the sample we took? And what we need to do is, let's account for this variation, the variation in the sample mean. with a confidence interval. Interesting idea. So that brings us to step 3. Use the stuff in your sample to build a confidence interval. So I'm going to tell you, I went ahead and did this for us. So I took the sample, I went ahead and calculated this for us. I'm just going to save us time and tell us what the confidence interval is. The 95% confidence interval around our X bar is this. Which brings us on to step 4. Ask, is the null value in the confidence interval? So the step 4 really gets down to the meat of why we are doing this the way that we're doing this, and gets down to the meat of what we can and cannot say with our statistical tools. So asking if the null value is in the confidence interval, or is, in this case, what was it, 9.93.29? Why we ask whether or not it's in the confidence interval is because we are 95% confident that the true population average in 2012 is in our confidence interval made in this way. So if our null value mu is not in the confidence interval, we reject the notion that it is the true value with 95% confidence. That is, in fact, maybe I'll just go ahead and finish this and I'll dive in. That is, we're 95% sure that the real truth is in this confidence interval. So if our null value isn't, it cannot, therefore, be the truth. Okay? So we were 95% confident that our confidence interval would capture the true population parameter, the true population average. So if we make this confidence interval, and it turns out that the value that we proposed as the true average is not in it, that means we're 95% confident that our null value is not actually the true population parameter, right? We are 95% sure that we captured the real truth. So if our proposed truth isn't in there, it can't therefore be the real truth. If that happens, we say we reject the null hypothesis. We reject the notion that our proposal is true in favor of the alternate hypothesis that, frankly, it isn't true. So in contrast, so this is the case when mu is not in the confidence interval. So what if it is? In contrast, if the null value is in the confidence interval, we aren't sure what to think. Without sufficient evidence, the null value remains innocent. And we fail to reject the null hypothesis. So if we made a confidence interval and our proposed value is not in the confidence interval, then we're pretty sure that our proposed value isn't actually correct. But if it is in the confidence interval, then we don't really know what to say. It doesn't actually mean that our proposed value is true. It just means that the data that we collected wasn't sufficient evidence to conclude that it isn't true. And that is actually a very important nuance in statistics. So maybe I'll write this down. A small but important nuance. And that is, note that this does not mean that the null hypothesis is true. We just said that we couldn't conclude that it isn't true. This is important because the null value may be subjectively chosen. So the point here is that failing to reject a null hypothesis is not really evidence towards the null hypothesis. It's just saying that we couldn't disprove it. And that's really important because null hypotheses, you could choose anything. Like, what if I came to you and I just said, humph. The average is 95 minutes. And I'm not basing this on any evidence. I am just loud and proud and have a lot of opinions. And I just need everyone to know what I believe, which is it's 95 minutes. I should post it on Facebook or something. This doesn't have to be based on evidence. I can just tell you a value and maybe it's a hunch. Maybe it's just what I want to be true. But even though my reasoning for choosing 95 is what I truly believe to be the population average, we could nonetheless go through all of our steps. So we could say, okay, we'll assume that it is 95 with the alternative that it isn't 95, right? We can look at our confidence interval, which was and note that 95 is in here. So by the steps that I gave you, we wouldn't be able to reject my probably erroneous claim that the average is 95, even though I've set it on nothing. So you shouldn't believe that failing to reject a null hypothesis means that the null hypothesis is true, because it may just be a consequence of some ridiculous statistics instructor at UNC making things up, right? So that brings us back finally. I'm sorry, I kind of jumped around this. So our sample in this problem showed what? It was like x bar was equal to, actually I think it was 95 and then something else, 95.61. This is in the confidence interval. We fail to reject. So remember we noted at the beginning that 95.61, based on our sample, it's looking like runners are slower in 2012 than they were in 2006. But we don't have sufficient evidence to actually say that. It might look like it, but because of the random variation associated with the sample mean, we don't have enough information to confidently say that it has changed. Okay? So that's how these work. Innocent until proven guilty. And this is how you set them up, and this is how you make the judgment call. So let's see how much time we got. Oh, we have a bit more time. So let's circle back to the example I gave at the beginning. Recall that we wanted to know whether the article that claimed that the population average of spiritual journeys the claim that the article that claimed that the population average of spiritual journeys is 8.7 miles is correct. So now that we've talked about hypothesis testing, we have all of the tools to assess whether or not their claim in this article is a good claim or a bad claim. And what was step one? We would formulate our hypotheses. We want to know whether or not the true population average of lengths of spiritual journey is 8.7 against the claim that it is not. Right? Step two, take a sample. Which our friend did for us. She did it, I believe, in the problem. Step three, make a confidence interval, which I believe she made for us as well, and it was this to and then step four, is the null value in there? The answer is it isn't. So we were 95% confident that the truth was in there, and the claim that 8.7 is the truth we claim that 8.7 is the truth, but 8.7 isn't in there. So we're 95% confident that this isn't actually the truth, since the truth is in there and we've observed something outside of there. So in this case, we reject the null hypothesis, which basically means that article is bogus. So you'll note rejecting the null hypothesis is usually the more fun conclusion to make because you get to say things like this, right? Whereas failing to reject, you don't really get to say anything at all. But this is an example of a very well thought out, a problem, a sample, a proposal, a well thought out assessment of that proposal, and a conclusion. Okay? So as mentioned before, hypothesis testing is something that is used in almost every field. So this is a pretty hot topic, and we're going to spend a lot of time practicing it and hopefully gain a very deep understanding of it. One thing I want to mention at the very end here just like how we could tune our confidence intervals to be more or less confident, we can tune these as well. We could do a 99% confidence hypothesis test. Or a 90%, etc. And as you might imagine, saying that you're 99% confident that the null hypothesis is false is a lot stronger of a claim, right? It's a lot more convincing to somebody that you're trying to convince, hey, this null hypothesis doesn't make sense and I'm 99% confident of this. That being said, if you increase your confidence, you're going to increase your confidence, you're going to widen your confidence interval, which means it's going to be less, you're going to reject values less often. So 99% confidence is kind of at the cost of how much you can really say, right? Something to think about, how these relationships kind of all interconnect. So that was actually about it for this lecture. Are there any questions? Wow, you're all killing it. So I will stick around if anyone wants to talk about anything. I should mention the homework for this class will be posted at 4:30, and I'm hoping to get the lecture video up before 5. I'm really sorry it's late today. So thank you, everyone. I'll stick around.